this seminars and lectures on quantum technologies will last till 19th June, and they will be referring to superconducting quantum technologies and to superconducting quantum technologies and to interlinks between those two technologies. I can prepare I already have constructed the interface, so we can talk about this interface. And also we welcome new guests and new people from outside, and we also welcome new talks. So if anybody has some suggestions, please send me an email. So let me move on. So basically, last week we discussed this RCSJ model, and this was basically the discussion was on. Yeah, I have it, so I will share it. So basically, discussion was on the essence of Josephson effect. And perhaps now it's time to refresh the last lecture on this Josephson effect. So let me briefly remind what was described last week. So basically, we have two quantum systems, left and right, and the quantum systems are in quantum coherent state. And they interact in a perturbative way. So basically, one can describe the Hamiltonian of such system as Hamiltonian of left side, of right side, and the interaction Hamiltonian. In a very practical way, it can be a tunneling in Josephson junction. So the Josephson junction is such structure as here. So we have left and right superconductor. We have some tunneling barrier, or we have a superconductor with a narrowing. So either we have a tunneling Josephson junction or a weakling Josephson junction. So this, in this case, yeah, welcome to. In this case, the superconductors interact much stronger. So this interaction does not always seem to be perturbative. And basically, so basically we have a tunneling Hamiltonian, and we can write it. So two quantum systems are orthogonal. So left is orthogonal to right, as it's written here, and the states are normalized. So in a sense, we have orthonormal quantum states. Basically, if we write the equations, we have the Hamiltonian for the system in such form. So we have diagonal terms which describe self-energy in the sense of left and right side. So this is in case of isolation of two quantum systems. And then we have a tunneling rate. And basically we end up with such type of two coupled ordinary differential equations. And now as a state of left system, we take, in case of superconductor, we take density of Cooper pairs on the left side and the phase. So this is the manifestation of quantum microscopic effect. And also we take a quantum wave function of the right system, so which is the density of Cooper pairs on the right side and a global phase of this microscopic wave function on the right side. What happens is that if we continue this relatively simple algebra, I discussed this problem last week, we end up in so-called Josephson relation. So we have the current, that this tunneling current is proportional to the sign difference between left and right wave function. Wave function of the right system and left system. So this is formalism that is valid for superconductors, superfluids, Bose-Einstein condensate, and so on. So systems that have manifestation of so-called macroscopic quantum effect. Let's say many of these cases of manifestations of macroscopic quantum effect. All right, so on the other hand, we also observe, maybe on the next page, yeah, so we observe that, so this is the current that flows via a Josephson junction. So T stands for tunneling, Hamiltonian part of tunneling. This was on anti-diagonal. Then we have a superconducting order strength. If it's the same on both sides of superconductor, then it's simply C square, as it's shown here. So this tunneling barrier depends on the thickness of insulator, for example. So if insulator is very thin, the tunneling rate is much higher, and if the insulator is quite thick, the tunneling rate is much smaller. So, so in a sense, we arrive to a so-called DC Josephson junction, DC Josephson effect, and which is expressed that by this phase difference between left and right. So this is a new quality in electrical engineering as well, since in most cases, current was driven by electric field in semiconductors. And here, actually, introduction of magnetic field can introduce the current. So this is very much manifestation of London equation for current. So in London equation, we have a current density that is proportional to vector proportion, vector potential vector, and this is deep connection with quantum mechanics. This is in a sense the same effect as observed in the probability current in Schrödinger equation. All right, so what happens if we consider this? If we solve these equations algebraically, we come to a very nice relation, which says that dynamics of phase difference between right and left superconductor is driven by the difference of eigenenergies of left and right system, and there is another term which is introduced here, which describes asymmetricity between left and right superconductors. So NL is density of Cooper pair on the left side, and R is density of Cooper pairs on the right side. So if two superconductors are, how to say, deeply asymmetric, this part is prominent. If they are symmetric, this part vanishes. And what is also important is that eigenenergies of left and right system can be controlled by external voltage applied in very delicate manner to left and right superconductor. So it turns out that we end up in so-called AC Josephson effect. And I would like to stress that if you have asymmetric superconductors, left and right, what happens is that left and right, we have naturally built-in oscillator in such system. So we have oscillator with no dissipation, kind of type of oscillator, and later it can be used in electrical engineering as so-called voltage-controlled oscillator, VCO, as it stands in superconducting electronics. So simply by applying very small voltages, usually in range of millivolts, we end up with control of frequencies in range of gigahertz and terahertz. So there's also a way to generate a hertz radiation by Josephson effect. So this is a very prominent feature. This model, which was introduced last time, we can also have temptation to introduce the imaginary part of this tunneling matrix. And it will modify our equations for the Josephson current. So there's not only sine term, but also cosine term. And this cosine term will be also connected with dissipation takes place. Also, this modification is visible in case of AC and Josephson effect. So basically, we have cosine and sine term. That's the difference between last time. And again, this sine cosine term occurs only in non-symmetric superconductors. So what is central conclusion from those considerations that rely on Hamiltonian approach, of course, phenomenological, but still, is that we can end up with, in a circuit model where we have Josephson junction and there is a current flow without dissipation across Josephson junction, so-called superfluid component, where Cooper pairs flow without dissipation, and we have a dissipative current, a resistance, and then there we have, of course, resistance in such kind of system, and capacitance. So basically, we have a ohmic law that coexists with London relation, and normal component of current is flows via these two sectors. So this model is already well adapted in SPICE software. And many engineers already designed Josephson junction systems, electronics with 100,000 Josephson junctions on one chip. I have a great occasion to work with such group in Japan for 1 year. All right, so this was just a summary of last presentation from last week, and now we want to move to something else, which is simply which will describe this quantum circuits and quantum technologies in a different manner. So first concept which I want to introduce is concept of washboard potential. Maybe I will use my whiteboard and I will simply all right, so let's say all right, so now I'm kind of okay, so I will share it. So we want to describe now the concept of washboard potential, and I will just do it in a second. So we will use this our knowledge. So I believe now the whiteboard is does everybody, as I can see on this whiteboard. All right, maybe different way. All right, so yeah, Radek, can you see this whiteboard right now? Right.
Yes, I can see.
All right. So what are equations of motion? So from last time so we have so we consider Josephson junction. This is the most prominent of use of macroscopic quantum effect in circuits. So this is nice to know. So we have such case that we have two superconductors and insulator. So we have a phase one here and phase this here. And what is essential for us is this phase difference. And the total current it was projected to, oh, somebody is yeah. So we have situation as here. And then I will remember this superconducting current was given as here. And then there was this voltage So this was such relation. Okay, maybe h over 2e. Yeah, so this is so-called between 1 and 2, 1. And yeah, this is 1, 2. Yeah. So then due to Ohmic law, we have this resistance and then what we have is, yeah, this relation. And in case of capacitance, we have Q over E is equal to C. So this implies that current is C VDT. So this component of current is nothing else as yeah. So this is simply equation for damped harmonic oscillator, nonlinear harmonic oscillator. It can be harmonic oscillator if phase difference is very small, so sign of phase difference is the same as phase difference. And so what's interesting to notice is that we can construct the, so this is like equation of motion. Equation of motion. And now we want to refer to this Hamiltonian description of effective Hamiltonian for this system. So how we can think of on this equation. So maybe I will just give you some of the hints. So at first let us fix is equal to E is equal to constant. And then so how we can deal with that. So the trick is to multiply all sides by this derivative. And then what happens is that we have such a system as given here. And then what we have here is Pt times Pt. So let us forget that, let us put no dissipation in the system. So we have two superconductors with infinite resistance. So we can have a, let's say, C1 SC2. So this term will drop. And now, what we can write is that the system is nothing else as dt over dt and minus cosine phi plus 4a c, and we have dt square. As you know, in Hamiltonian approach, there is no dissipation. And so we have such system as being here. And what is interesting is that we can postulate, so if we integrate this with time, we will see that we can come into a very nice conclusion. So in a system without dissipation, there is a conservation of energy. So we can say that this is constant with time. And that's very important result. So this is our new Hamiltonian. So actually it's our phenomenological Hamiltonian. And this Hamiltonian has, so far it's a kind of quasi-classical view. So basically, the Hamiltonian has phase difference and a kind of velocity of phase difference. And we will refer to this as to Hamiltonian where we have a harmonic oscillator, where we have position and moment. So it's very important that position will correspond to phase difference and momentum will correspond to velocity of phase difference. Something else over here. And obviously we can linearize this, so we can always write cosine phi in the first approximation minus so we will get harmonic oscillator. For very small phase difference, we have harmonic oscillator. And since we are dealing with quantum effect, this story becomes more complicated. Because, so this is quasi-classical picture. And what is important is that if you have current voltage characteristics, what happens is that there is current and voltage. And as you know that this voltage is from this equation is nothing else as velocity. And here, this current has two components, but these two components are specified here. So this current may be either simply, but of course we are neglecting this term. So what happens is that we have a function of phase difference, and basically experimentalists observe something like this. So this is nothing less as something like this. So this is for tunneling junction. So this is analogical with situation where you have a harmonic oscillator and you have a momentum and position. So this is, you get as such type of system evolution in harmonic oscillator without dissipation. So this is very big picture. And now there starts to be, so this is classical picture, but now we want to go into quantum effects. So what we know, so if you have a Hamiltonian of harmonic oscillator, classical Hamiltonian, if you want introduction of, want to introduce canonical quantization, you need to have a certain relations. There is commutation relation for classical oscillator. And now you need operator of a phase difference, and then you need operator of velocity. So so basically you have a number of particles on the left and right side and velocity. Maybe it's also, before moving to the third way, if we have two superconductors, there's a jump of Cooper pair. This Cooper pair jumps back and forth. And so what happens is that we have essentially, we have we need to have number of particles and phase difference on each of the sides. And there must be a commutation integration fulfilled.